Hello, this is Mr. McMurray, and welcome to Physics 1415, our next to last lecture, or close to the end is near. It's going to be a very enlightening night, hopefully, and I'm not sure whose bright idea that pun was, but anyhow, we will hopefully brighten up your life today. All right, so let's talk a little bit about light. We're going to have two chapters actually on light. This one's going to be more about reflection and colors. And the second one will be more about lenses and polarity and a whole bunch of other stuff. But light is enough stuff that we need to have two different chapters. All right. Now, first of all, light is an electromagnetic wave. And basically, if you have an electric particle and it begins to vibrate, it will give off an electric field. And that will send off a wave, a transverse wave, where it goes up and down, up and down, up and down, like so. But we know that when an electric charge is moving, it creates a magnetic field. So if that one's going up and down like this, there will be at right angles going toward you, back away from you like this, a transverse wave going that direction as well. Okay, and therefore it's an electromagnetic wave because you have both going on. You have this is like, for example, the electric field vibrating this direction, and then the up and down is magnetic, or vice versa, depending what angle you're looking at it from. But they're always going to be at right angles to each other, and you have both of them, and that's why they're called electromagnetic waves. Now, there's a whole spectrum, and you've probably seen this before. Starting at the low end down here, these are low frequency. Why? Because there's not very many vibrations per second. Now, we say not very many. This might be 1,000,000 per second, or over here is 10 million, I think. All right, and this is up already in the trillions. And by the time you get over here, trillions is here, and then billions I meant there, and then trillions and million trillions, and numbers that are so big we have a hard time really wrapping our head around them. Okay, but basically the low frequency, um, basically, notice they have a long wavelength. Okay, so long wavelength, and these may be a football field in wavelength. Time it goes up and down and back again, you could take a whole football field. Okay, these over here are measured in like nanometers, microscopic, even below microscopic size. Okay, so notice that when you have a big wavelength, you have low frequencies. When you have short wavelengths, you have high frequencies. Notice that these actual wavelengths do not uh, represent the actual size they are in real life. Okay, but also notice that as the frequency increases, the energy increases. At the low end, we have radio waves. And somewhere in the middle here, you would have TV waves. You have AM radio, which has the lowest frequency. Then you would have TV. You used to have two dials on your TV, a UHF for ultra high, VHF for very high frequency, and that was usually channels through 1 through 13. Okay, then you had to set it to VHF, and it would go to very high frequency, or maybe I got that backwards. No, I'm sorry, UHF. Yeah, UHF would be the higher one. And it would go from 13 all the way through 60, 70, whatever, however many channels there were available. And that would be the ultra high frequency. You already had very high frequency, so now you had to go higher than that. Okay, and somewhere in there in between those two, you actually had um, uh, FM radio. So you had AM, the VHF, and then you had FM, and then you had the very high frequency ones. Okay, now once you get to that, you get to microwaves. Okay, compared to the radio waves, they have very short wavelengths. I guess is how they got their name. All right, microwaves. We know this is besides your microwave oven, this is also your cell phone signals are done by microwave towers. Okay, they're sending out microwaves. All right, and then we get to infrared. Infrared is actually a radiation. We say it's heat. It's not really heat. When it hits objects, it creates heat, but really it's just a microwave. It's a wave, an electromagnetic wave, that when it hits us, we feel it as heat. Okay, but the wave is not actually hot. The that's why you don't feel the heat as it goes through the air, infrared. But when it hits something, it causes heat. And so we talk about infrared lamps and goggles at night that can see infrared. Okay, then you have the visible light. Okay, which is Roy G. Biv: red, orange, yellow, uh, green, blue, indigo, and violet. Lowest frequency is red. Highest frequency. This is all that we can see. Technically, this is all the same kind of radiation of energy, electromagnetic wave. We can just only see this part of it. Some animals can see infrared, some can see ultraviolet. Bees and insects, for example, identify flowers that look different to them because they can see their ultraviolet light, which we cannot see. Okay, ultraviolet is also getting to be more dangerous. Most ultraviolet light doesn't get through the atmosphere to us. We'll talk about why later, but that does can cause sunburn and can even cause cancer if it does damage to the cells and particularly to the genes that control cell division. You can get skin cancer from it. And then X-rays, which are the next highest, and the very highest gamma rays. Both of these are extremely dangerous if you're exposed to it over long periods of time. High energy. Okay, radiation that we use to treat cancer would be these kinds. Ironically, these kinds of radiation can also cause cancer. So anyhow, if they damage the cells. But anyhow, basically all electromagnetic waves, notice despite the frequency difference, the speed they move this direction or forward is the same. They move at the same speed. We talk about the speed of light, but we could talk about the speed of radio waves or microwaves or infrared or gamma rays. It's all the same speed. The frequency just has to do with how much they're vibrating back and forth. Okay, that's as they travel, but they're traveling the same speed in a forward direction. Okay, so the only really difference is their wavelength and therefore their frequency. If they have a long wavelength, they have a low frequency. If they have a short wavelength, then they have a high frequency, and that has to do with how much energy. There is no dividing line that makes a radio wave different than a microwave or a microwave different than an infrared. We have just boxed them off in these little categories, but technically they're the same kind of electromagnetic wave, and they just gradually change their frequencies, okay? And so there's really no difference between them other than that, okay? Notice these are completely different than sound waves. Sound waves do not travel at that speed. Sound is much slower than electromagnetic radiation. All right. Now, let's say this comes along and it hits a piece of glass. Let me get some glass. I have some right here. All right. If I have radiation or electromagnetic wave that hits the glass, there are several things that can happen to it. Okay. Some of this light, okay, may be reflected. All right, or hit it and bounce back, and that's why you can see the reflection of the light fixture, boom, coming back because it's hitting here and then it's bouncing back off. Okay, usually this is where it excites the electrons, but rather than shaking the electrons, the rest of the atom, or the electrons next to it, they just bounce the light right back off. Okay, however, that doesn't always happen. Some things, like say my shirt here, is what we call opaque. Okay, and what happens is the light is there, it does excite the electrons, but they just absorb it basically. Okay, they absorb the electricity, okay, the light. Okay, the light energy. They absorb that light energy, and none of it is re-emitted or given back off in any way or reflected off. Okay, well, I say that some is reflected back off. The blue color, for example, that you can see coming from this, or purple, whatever it is. I'm colorblind. Okay, seriously, we'll talk about that later. But anyhow, if it's opaque, basically it absorbs it. Okay, and if it emits it, it emits it just like the same kind as it was coming in. Okay, but if we have something like glass, glass is transparent. Okay, transparent means the energy hits it. The electrons begin to vibrate, but relatively quickly. And so instead of having time to bounce around all the the atoms next to them, they just kind of pass it on to the next one, next one, next one, and then it comes out the other side. Okay, so electrons on the edge here, boom, pass the next one, and it comes out the other side, and it comes out as the same frequency of light or whatever as it was coming in. Okay, that means it's transparent. Just lets the light go right through. That's why you can see through it. However, it does take time for it to hit from one atom to the next atom. Okay, we're talking billions of a second, but still, it takes some time, and so it slows down when it goes to the glass. Now, this will be important when we talk about lenses next chapter, but it's going to slow down when it goes through this. Okay. Normally we say it goes at the speed of light, which is c. The letter C stands for the speed of light. Don't ask me why it's C. It's roughly about 300,000 kilometers. okay, per second. Okay, very, very fast. But technically, that's in a vacuum. Okay, once it hits the atmosphere, it's a little bit slower than that. Okay, but it's pretty close to c. So we just say the speed of light, and we still call it 300,000 kilometers. That's about 150 miles per second. Okay, if it makes you feel better. Okay, only 150 miles per second. All right, if it hits water, which is transparent, okay, it slows down to 0.75 or 3/4 of the speed of light in the vacuum. And then glass slows it down a little bit more to about 2/3 or 0.67 c, or the speed of light. All right, diamonds slow it down even more. And because it slows it down, it's going to make it bend. And we'll talk about this more next time. We call it refracting, or slowing down, because it bends. And that's one reason why diamonds are more sparkly than, say, glass. All right, and if you get your girlfriend a glass ring versus even cubic zirconium versus a diamond, she may be able to tell because it may not be as sparkly. And that sparkly part has to do with the way it slows down the light and causes it to bend and bounce off in different directions and give all that nice little sparkly effect to it. Okay, but basically, that's what happens when it goes through a glass. It passes it on from atom to atom. It comes out the other side as the same kind of light or energy, but it has slowed it down. Okay, now we have translucent. We're not going to worry too much about that, but the light fixtures up here, for example, will be translucent. If I look at them, I cannot see the light bulbs in there, so it's not transparent, but it does let most of the light through, and so that's what we call translucent. Okay. Now, if we have UV light were to go through this glass, okay, it hits the atoms and it gets them really excited because they vibrate at the same frequency as the UV light. And so they really start bouncing around. But instead of passing it from one to the next like transparent objects do, they have so much energy, it just it passes around there, and it stays in the glass so long it doesn't pass out on the other side. It just stays there or is pushed back to the other side, and so it's actually opaque. So we would say normally to UV light, we think, oh, glass is transparent, and it is to the light we can see, visible light. But when you get to ultraviolet, it is actually opaque and will not let it go through. The same is also true of infrared, which we think of as heat. Okay, so say we have a greenhouse. Okay, well, the UV light hits it and can't go in. Okay, so that's not going to heat up the greenhouse. Well, what about infrared? Well, the infrared, which we know when it hits things, gets them hot, it will heat up the glass maybe, but it won't go through. It can't go through. It doesn't get passed on through inside the greenhouse. So it says, well, then how do greenhouses get hot? Well, visible light can go through. Okay, once they go through, they hit pots and tables and whatever else is inside the greenhouse. When they absorb it, they absorb the energy and usually retain it as heat. And if they give that off, it gives it off as infrared. Well, that infrared, we know, can't get out of the greenhouse. So the more visible light comes in and is changed to heat when it hits objects, then it creates infrared, and that infrared is trapped inside there. And that's the greenhouse effect, okay? And that's why greenhouses get hot, okay? And you can grow plants in the greenhouse, even if it's cold outside, you can still get enough heat in the greenhouse to keep plants alive there. All right, so glass, we think about transparent as being able to see through. It depends what you're talking about. It is opaque to infrared and it's opaque to ultraviolet, but it is transparent to visible light. Okay, so let's see, anything else? Metals, on the other hand, are a little different. Metals, if you remember, their electrons just kind of go flying around all by themselves. So when they start vibrating, they don't pass it to the next atom because they're just kind of moving around between atoms anyhow. And so instead of being passed on orderly, like you would expect, like heat, energy, and electricity is, they'd actually get so excited they just bounce it right back out and they reflect. And that's why we say metals are shiny. Why? Because they reflect light. Okay? All right. And so what else? Basically, let's talk about the atmosphere. We said basically it is opaque to the high frequency UV light, the really dangerous stuff, fortunately. So most of it does not come through the atmosphere and get down to us, but some does. And that is why you have to put SPF 55 or whatever the highest thing you can come up with is to protect your skin from that UV light that comes on through. Clouds are semi-transparent. So that's why on a cloudy day you still get sunburned, okay? And you can still be damaged to your skin by the UV radiation. Why? Because they can still pass through the clouds, even though not as much maybe as you would otherwise. But if you're like on the water, it's cloudy, the light comes through, then it reflects back off the water up in your face, and so you can get a lot of the UV sun and do damage even on a cloudy day. Okay. All right. What else we need to talk about? Reflection of light. Okay. The law of reflection states that the angle of yeah. Okay. What is the law of reflection? Let's talk about that for a second. Okay. Reflecting is basically bouncing off of, right? Okay. And so, let me see if I can get this. Okay. If this is your mirror here, okay, now technically it goes into the glass part of the mirror, and then on the back of the mirror there is a reflective surface. Used to be mercury originally, but that's kind of dangerous stuff. So they use other things now that are shiny, metallic looking, and reflect good. You can even get plastic mirrors that reflect. Okay, but we're just going to show the mirror as a flat thing here. Keep in mind, first part of it's glass. It lets the light go through it, and then it hits the reflective part on the back. All right. If it's coming in, that's called the incident ray because it's incoming. And where it bounces off is a reflected ray. If we were to draw an imaginary perpendicular line, we call that the normal. If you remember, we had a normal force that was perpendicular to the surface pushing down. Well, this is the same kind of thing. A perpendicular line is called the normal. Okay? And so the incoming ray, if it's coming at a certain angle from the normal or a certain angle from the mirror, either way you want to look at it, then the reflected ray is going to be at that same angle that bounces off. And so we can always predict where we can see something. If we see something in a mirror. All right. All right, let me set up something and then we'll get right back to you. All right, if we have something like this right here, a flash, and I have my piece of glass right here. If I look at it, and I don't know if y'all can see this or not, but I can see the reflection of a glass back here, okay? And if I put where it looks like my finger is going in the middle of that, like I said, I don't know if y'all can see that reflection very good or not, but if I put my finger in it, if I move the glass, it turns out that my finger is exactly the same distance from it to the glass as this is. In other words, when the light reflected off, it makes it look as though I see an image back here that looks like it's just as far back behind the mirror as this one is in front of it. Okay, and that is considered a virtual image. Why? Because is there actually something back here that's sending light to your eye that says, oh, there's a glass back here? No. Okay. There is here, so this is a real image. But the one back here, it looks like there's light coming to it, and you see it in your eye. So when you look at a picture of something in a mirror, okay, let's just do that one right there. See, all right. If you look at the image in the mirror, it looks like something back there is sending light out to your eye, but there's really nothing there, of course, back here. And so that's actually an optical illusion, all right, or that is called a virtual image. It's not a real image, not really something sending light from that spot. Okay. All right. Now, on the other hand, let's see if I can get this where you see it. All right. If you look at this, it looks like I've got a little dome here, and right on top of there, there's a pig. All right. But if I put my finger in it, oh, it's not really there. Okay. So it says what? So first of all, is this a real or a virtual image? Well, the fact is, I am seeing light from this spot right here that comes to my eye. So that is considered a real image, but there's not really anything there. Okay, this is actually a curved mirror here and a curved mirror here with a little pig at the bottom of it there. Okay, and that is reflecting light, and it's reflecting it right here so that it looks like, I don't know if I can get that good where you see it, but it looks like there's actually a pig right here. Okay, and so that is a real image because there's really light coming. It's being reflected by that round mirror, but it's being reflected back to my eye. So that's considered actually a real image. We call it a hologram because it looks like there's something there, but there's not really. Okay, but there is actually light coming from that point. It's being reflected from all sides of the pig, and that's why we see this 3D image. Okay, and so that is a real image, even though there's not actually a real pig there. Okay, but there is light coming from that spot. Okay, now let's do some more stuff with mirrors real quick. Let me pause. All right, if you've seen a kaleidoscope, you've seen one of these, but this is just three mirrors, three pieces that I've taped together to make a triangular prismy looking thing. Okay, and here's the deal. If you look down the middle of it, let me see if I can get that. Hard part. Okay, let me see if I can get that where your camera. And as you rotate it, you can see whatever the pattern is at the end, and you see some of it straight on because I have like my fingers here at the end. And then as you rotate it, you see the reflections of them, and it makes kind of different patterns. The neater thing you have here, the better it looks. But that's basically a kaleidoscope, and it's because you're seeing all these different reflected images at different angles, and as you turn it, they rotate, and a lot of times they'll put like colored sand or marbles or something on the end down here to give you some really neat patterns, okay? And that's basically based on the laws of reflection. Okay, another neat effect is, say you have a mirror that has a hole in it. Okay, I'm going to put that hole up here on next to the camera so it'll fit over there. Okay, and now if I put another mirror at it, well, light is going to bounce back and forth between the mirrors, and you can get a succession of smaller and smaller reflections back and forth. Okay, and you can get almost endless. Okay, now if you actually do it yourself, you can look at it and you can get more and more, just almost an infinite number of mirror images being reflected back and forth, back and forth, back and forth, smaller and smaller. Kind of cool because kind of endless reflection between the two mirrors. Okay, you see a reflection of a reflection of a reflection of a reflection, and that's also kind of cool. All right. Now, if I'm looking in a mirror, I move my right hand, and you can't tell that, but I'm moving. This is on the opposite side of me because I'm looking at the screen. It looks like a mirror image, and so if I move this hand, usually it's this one right next to it that goes across. If you touch it, when you reach forward to the mirror, okay, you touch the mirror like so, and you see, um, yeah, okay. So if I, yeah, I don't know how to explain this without really showing you, but you know how it is. If you wave, you see the same side of the mirror, which technically, if there's a person facing you and that arm was waving, it would be your opposite hand, right? Well, there's a way to get around that. Okay, if you take two mirrors and you put them at right angles to each other, okay? I put tape on this one, like a book, okay? But put them at right angles to each other, all right? And if you do that, you can actually do something on one side and it will show up on the opposite side, okay? So for example, if I'm looking at it and I wink this eye, instead of that eye winking in the thing, the other one would, which is right. If I looked at a right eye blinking and someone's standing at me and they blink their right eye, it'll be on the opposite side. Okay, and so if you look into the mirror and do this and you blink, it's kind of weird because we're used to, if I look at the mirror, I blink, I see this one, then the one on the same side of the mirror blinks at me. Now the other one does. Why? Because when light hits this, so light from my eye hits this mirror, it bounces to this mirror and then it comes back to my eye. And so it actually flip-flops my image. We talk about a mirror image, like it's been flip-flopped. Well, it flip-flops it right back, okay? And you can actually see it. Now that's kind of disconcerting to people because if you've looked in the mirror, say you have your hair parted on one side, you're used to seeing it on that side. Well, everybody else really sees it as if it were the other way, and you kind of can see that you look a little different than you think you did. Not usually a major thing, you just kind of flip flop, but it does kind of throw people off sometimes. All right, okay. Now, sometimes instead of a flat mirror or a plane mirror, plane just means not fancy. It just means plain, as in it's flat. Okay, like a plane in geometry. Okay, now if we look at one that's been curved, this one curves in, so it's a concave because it goes in like a cave. If you look in that mirror, you'll notice the lights are on the bottom and the floor is on the top. So from a distance, if you're out, this would normally focus light right out here in front of it. That's called the focal point. If you're outside that focal point, farther away than the focal point, then it makes everything upside down. Okay, and it makes it smaller. You'll notice you can see most of the room. Okay, so it makes things upside down and smaller. Still a virtual image. Okay, but if you get it up close, some point things flip over, and the right side up, you can see the cabinet in the background. But notice they're a lot bigger. Okay, this up here you can see is the little symbols at the top. It actually is bigger than it was before. So if you're inside the focal length, things are right side up and they're enlarged. This is why people use this for makeup mirrors, okay? Or what this one is, someone at their desk can put a makeup mirror. And if you get it up close, it makes you look so close. You can see every little pore. And of course, that makes you girls want to run out and buy makeup because no one's pores look good that close up. I don't know if it's a conspiracy to do that, but that's definitely one of the effects of it, okay? It really blows it up close. But if you take it from a distance, then it flips things upside down because the light rays that are reflecting have bounced and crossed, and now they're upside down, and it makes it look like something a lot smaller in the concave mirror. All right. What about a convex mirror, one that curves out? Well, let's see if we can get one of those. All right. If we have a convex mirror, this one curves out. I don't know if you can see that. It's not a whole lot, but it curves out. Okay. And if you look at that, once again, you'll notice that it shows everything right side up, much smaller. It shows you a much wider view of the room. Okay. A lot of times you will see this in the corner of a convenience store, and someone at the front desk can look at that and then see almost the whole store and see if anyone's trying to shoplift or something like that. The other thing is on buses. A lot of times on the bus, that'll be over here on the side here, so that they can see the whole side over there where people are trying to pass them, and they may have it on both sides so they can see cars coming up behind them on either side. Okay, and so a convex mirror is going to show a smaller image. That's why it says and farther away, looks farther away and smaller, but it gives you a wider range of view, so you see more. But that's why you have the little warning on there. Objects in this mirror may be closer than they appear. Why? Because it makes things look farther away so it can give you a wider angle. But it comes in useful for that. Okay. Now, in order for mirrors to work, it really depends on if they are what we call specular or a diffused reflection. Okay. Basically, the smoother a surface, the better it will reflect. All right. But how smooth is smooth? Well, it depends. It's considered specular if any irregularities, bumps, if you will, are less farther apart than 1/8 of the wavelength. Okay, well, most of light wavelengths are very, very short wavelengths. We're already in that where they're like you know, millimeters or nanometers. Okay, so something to be less, to not be to be smooth and be less than 1/8 of that wavelength, they've got to be very, very smooth. And so things tend to have to be really smooth. Glass will reflect only about 4% unless you coat the back of it, and then you get a much better reflection. Now it depends also if there's light coming through the mirror glass. If there's light behind the glass that interfere with the reflection, then you don't see it as good. If it's dark, like you're inside the house at night and you're looking outside, then you'll see your reflection in it pretty good. Why? Because all you're seeing mostly is the light being reflected back. There is no light hardly outside in the dark, so you'll see more. Polished silver, on the other hand, will reflect about 90% of the light hitting it. And that's why they used silver to coat the back of mirrors originally, and then they've come up with safer things since then. But other things like radio waves are very long. We said some of those can be as long as a football field. Okay, and so just for example, here's paper close up. You can see it has a bunch of irregularities. And so paper does not reflect very good because you've got very small wavelengths of visible light, and there's a lot of bumps and stuff in there, and there's no way it's ever going to bounce off. But on the other hand, you can see this big old radio telescope, and it's basically just a framework of metal. It has big holes in it. But if the wavelength is a football field, well, 1/8 of a football field is still 12 yards. So if there's smaller holes in it, it looks pretty holy to us, but to a radio wave, they cannot get through that. They will get reflected back. Another example is microwaves, which are, I believe, usually about 3 feet wavelengths. Probably depends a little bit on the microwave, but you got all these dangerous microwaves. What's protecting you from that? Well, in the front, you have a glass door with holes in it. Okay, what's keeping it from there? Well, the fact is that these holes are less than 1/8 of a wavelength, and therefore, if a microwave were trying to go through that hole, it would, by the time it traveled that distance to get through it, it would hit part of it and be reflected back in. And so even though this looks dangerous, like microwaves can just come flying through this, to a microwave, this is smooth and it will bounce right back into the microwave. Okay, so no, you will not get fried by sitting in front of your microwave. Okay, now if you stick your head in there and somehow shut the door and made it work, then that's a different story. But you're not going to be fried by the microwaves coming out because it's considered specular. All right. Um, now, um, I'm not going to talk a lot about the angle of refraction. Basically, if light hits a surface it goes from one kind of medium to another, like say air to glass, like in my glasses here. Okay, if it comes straight on, perpendicular to the surface, it's just going to pass right through. It's going to slow down when it hits the glass, and it's going to speed back up when it gets on the other side. Okay, but if it hits at an angle, so part of it hits the glass and slows down, then it's going to turn. I think last week we had the little wheels, and said if half the wheels slows down, it's going to make it turn in that direction. If this side is slower, it's going to turn. And so when it hits glass, like a lens, all right, especially if you have a curved lens, it's going to have to hit part of it first, and it's going to make it curve. All right, if it hits perpendicular, just goes right on through. Okay, same thing happens when it hits water. Okay, and this is why if you're trying to catch something underwater, you're above the water looking to spear a giga frog or something like that, or bowfish for fish that are swimming in the water, you have to adjust for that. Okay, I'm not going to go over that in detail here because I think you can look in the lecture and it talks about that, but you have to use that to help predict where it would be. Okay. And because it bends when it goes from the water to the air, the light bends, and so when it comes to your eye, it's coming in this line, but since it bent out of the water, things aren't where they look like they are. Okay, we're also talking about mirages. I'm not going to talk about that because I think that's in your other notes. But let's talk about light and color because we got some things here with light and color. All right, that we can show you that are kind of neat demos. Okay, so let me turn off lights and we'll see how this works. Unfortunately, it's not the greatest camera for light and dark photography, but we'll see how we go here. All right, so we're gonna try this color thing here. I'm not sure what taped or didn't tape a minute ago. I thought I had this taping and it apparently did not. Okay, so I have a red light here. I don't know if you can see that, if it makes me look red. Okay, we have a red light. We have a blue light. So it makes me look blue, hopefully. Okay, and we have a green light. I don't know if that'll make me look green or just be a mess. Okay, like I said, it's not the best camera for color photography in the dark, probably, but we're going to try it. Okay, now if I shine these on the wall over here, all right. So let me scoot this down just to try this. All right. All right, and I take this box of salt here. Hopefully, you'll be able to see the different colors on the wall. I don't know if you will or not. Hard for me to say. Okay, but basically, if I put it in front of the middle, and this is the blue light, so right behind it, there's a shadow that looks yellow. Why? Because it has no blue. If you have no blue, then you have green and red light, and it turns out that green and red light, when you put them together, make yellow. Okay, now on the left-hand side over here, you have no green because the green is over here. And so when you put it over on this side, there's no green. So it's only getting the red and the blue. So you get what we call magenta, which is kind of a purple color. Okay. And on the other side, it's harder to see this one. It's usually a real hard color to see. But you have no red. So you have green and blue. And that is called cyan. Okay. So basically what we've done is by making shadows like this, we've subtracted one color. So over here, we have magenta because there's no green. It's just red and blue, and it makes a purplish color, which is magenta. That makes kind of sense, we say. Okay, in the middle, there's no blue, but it turns out that red and green light, remember, they're additive colors. They add together, and so they actually make yellow. We're used to adding pigments together. We have a hard time getting our head around that one sometimes. But when you add colors, it gets lighter, and it turns out that red and green make yellow. And on the far side over here, where there is no red, you have blue and green, so you get what we call cyan, kind of a bluish green color. Okay, now if I put these closer together where they overlap, and I don't know if you can see these shadows up here, where the middle one is yellow because there's no blue. If it overlaps with the one over here that has no green, well, if you have no green and no blue, then it's going to start turning red, and you see those shade red. On the other side, if you have the no blue in the middle and no red over here where it's cyan, where they overlap, you have no blue and no red, then it turns green, okay, which makes sense. All right, now if I get it close enough, eventually it will overlap to a point where there's no green, no blue, and no red, and guess what? You have a black shadow, okay? So here's the deal. It turns out that colors that, well, we can call them opposite colors for one thing, okay? Because if we take out the blue, all right, if I take out the blue, now I just have green and red. And when we put those together, it makes yellow. So we would say that yellow, which is blue and green, excuse me, red and green put together, is the opposite of blue. Because if you take out the blue, you have yellow. All right. And so it's the opposite. But if I put yellow and blue together, now I have all three colors again, and it would give off what we call white light. So it makes white. So we say they're opposite colors, but if you add opposite colors together, it will make white. Okay? Because really yellow is just no blue. And so if you add blue back to it, now you have all three colors and you end up with white. Okay? If we get rid of the green, okay, then we have cyan. Excuse me, I'll try. Yeah, try that again. If we get rid of the green, we have blue and red. So we have the magenta, which is kind of a purplish color. Okay? And so magenta and green are opposite colors because you can't have green and magenta at the same time. But if you put them all together, then once again, they're going to combine to make white light. Okay, so they're both opposite, but they are complementary. Now, if I turn off the red, then all we have is green and blue, and they're going to make cyan or blue-green. And so they are, cyan is the opposite of red. And if you put the red back together with cyan, then you're going to get all three colors again, and it would make white light. Okay, I know that's kind of confusing, and we're used to thinking about adding pigments together, but when you add light, it becomes more light or brighter rather than getting darker because they're primary additive colors. Okay, we're going to try this over here again. This is kind of the same thing as we showed before, but we're just going to try it a little differently. Oops, we have some little lights this time, and we have a battery here. All right. On this side over here, we have a blue light over here on this side. So over here we have a shadow that has no blue, and if it has no blue, then that means it's going to be red and green, which is going to make it yellow. Okay. Now also though, all right, in the middle we have no green. It's right in front of the green light, so there's no green here. So it's actually kind of a magenta or purple color. Hopefully you can see that. Okay, now on the far side, there's no red. The red over here can't get over, so it's kind of a blue-green color or cyan. All right, now as we move the battery closer to the wall, this is the no blue side. The middle gets no green. So where these two shadows, no blue and no green, where they overlap, the only color left is red. And on this side, we have the no red, which is the blue-green cyan. And in the middle, we have the no green, which is the magenta. And where they overlap, guess what? We have blue. Okay, because if you have no green and you have no red, the only thing left is blue. And so the blue light is there in that shadow. Okay, but if we take this out, then basically we have white light on the wall, because if you have all three colors, then you're going to have white light. Now, if I put my hand there, you'll notice there's all colors of shadows in there, depending on which ones are being blocked out, and kind of cool. And so if you're in theater lighting, you have to think in terms of what's going to happen when we add these different colors of